factors affecting the rate of nucleophilic substitution reactions. Here are the important factors which is going to affect the rate of the nucleophilic substitution reactions. We'll talk in terms of SN2 first, and then we will move on to SN1. The most important factor which is going to affect the rate of SN2 reaction is alkyl halide. The nature of the alkyl halide is very important. Okay, remember when you talk about SN2 reaction, you're talking about the steric hindrance. Okay, primary alkyl halide will undergo SN2 reaction much faster than a secondary alkyl halide, and then only comes your tertiary alkyl halide. So because the primary alkyl halides and even the methyl halides have less steric hindrance, it is supposed to undergo the SN2 reaction much faster. The next one is the leaving group. We'll talk about this in detail, and we will talk about how the nucleophile is going to affect the rate of SN2 reaction based on two different things. One is the charge of the nucleophile and the other one is the size of the nucleophile. And then we will also talk about how this solvent is going to affect the nucleophilicity of the nucleophile. There are two different solvents, two different types of solvents, polar aprotic solvent, and the other one is the polar aprotic solvent. We will look into the structures of these of some of these solvents and how it's going to influence the nucleophilicity of the nucleophile. Now let's see how the leaving group is going to affect the rate of SN2 reactions. Let's first consider these four reactions. In all of these four reactions, you can see that there is a primary alkyl halide. So all of these are primary alkyl halide, and the only difference between these reactions is the nature of the leaving group. When you look into the relative rates of these reactions, you can see that with alkyl iodide, the reaction rate is about 30,000 times much faster than alkyl fluoride. Now, what is the reason? Why with alkyl iodide the reaction is much faster? What is the reason behind it? That is because iodide ion is the weakest base and it is going to be the best leaving group. When you draw the conjugate acid for iodide ion, it's going to be Hi, right? And similarly for fluoride ion, it's going to be HF. So now between these two acids, which one is the stronger acid? Obviously, it's going to be Hi because you can see that the pK value here is -10. Therefore, this is a strong acid, whereas this one right here is a weak acid. HF is a weak acid, comparatively weaker acid. From the basics of acids and bases, we know that a stronger acid will always have a weaker conjugate base. Right? So the I minus, which is the conjugate base of Hi, should be a weaker base, whereas the F minus is a stronger base. And the I minus is going to be also the stable base because of its larger size. When I minus leaves from alkyl iodide, it's going to be well stabilized because of its larger size where the negative charge is more dispersed than in the case of F minus, and therefore I minus is the best leaving group in nucleophilic substitution reactions, and therefore alkyl iodides are more reactive than alkyl fluorides. The next factor that is going to affect the rate of the SN2 reaction is the nucleophilic strength. Okay, now we have to understand the basic difference between basicity and nucleophilicity. When it comes to basicity is basically a measure of how well can act as a base, basically sharing its lone pair of electrons with a proton. So the lone pair needs to be shared with a proton, right? H plus. Whereas when it comes to nucleophilicity, it is a measure of how readily a nucleophile is able to go and attack an electron deficient atom such as carbon. Okay, so the lone pair is going to attack an electron deficient atom. So that is the basic difference between basicity and nucleophilicity. While the basicity is measured in terms of acid dissociation constant, nucleophilicity is determined or measured in terms of rate constant K. Now that we know the difference between basicity and nucleophilicity, we can definitely tell that in an SN2 reaction, it is the nucleophile which is going to take part in the reaction and not the base, where the nucleophile is going to go and attack an electron deficient atom. In general, if the attacking atoms are the same size, then stronger bases are better nucleophiles. For example, when we compare the attacking atoms in the first row of the periodic table, Let's say we have NH2 minus, OH minus, and F minus. Between these three nucleophiles, which one is the strongest nucleophile? NH2 minus is the strongest of all because it is the strongest base. Okay, this is the strongest base, and therefore this is the strongest nucleophile also. So when you compare the atoms which are exactly in the same row, then the strongest base is still going to be the strongest nucleophile. So NH2 minus is the strongest base and as well as the strongest nucleophile, whereas F minus is a weaker base and is a weaker nucleophile. And the second thing which is going to affect the rate of the SN2 reaction is the charge on the nucleophile. In general, a negatively charged atom is a stronger base and a better nucleophile than the atom which is neutral. So as you can see from here, we have OH minus and H2O, right? Both have exactly the same atom, oxygen. But here, since it has a negative charge, since it has a bunch of electrons around it, it is more nucleophilic than water, okay? Where these electrons can go and attack the electron deficient atom. Similarly, if you consider NH2 minus and NH3, they have exactly the same atom, and you can see that the NH2 minus is going to be a strong nucleophile because it is able to attack the electron deficient atom much more efficiently than NH3. If, however, the attacking atoms of the nucleophiles are very different in size, such as in the case of I minus and F minus, then there is going to be another factor which is going to come into play, and this another factor is called as polarizability of the atom. Let's consider two different species here, I minus and F minus. Between I minus and F minus, we know that iron is a very large atom, and because of which the electrons are farther away from each other in a larger atom, and they're not as tightly held as in the case of fluorine, right? And because of which they're also able to move freely toward a positive charge, making a nucleophilic attack on the electrophilic carbon. This is going to result in a greater degree of bonding in the transition state, thereby increasing the stability of the transition state. Right here, it is going to be more stable, right? Then here, this is relatively unstable because there is only little bonding between the fluoride ion and the electron deficient carbon. Now, the most important question that we need to ask ourselves is, does the greater polarizability, which helps the larger atom for it to behave as a better nucleophile, to go and attack the electron deficient carbon, is it going to make up for its decreased basicity? The answer is going to be dependent on the solvent. Let's now take a look into the different types of polar solvents. There are two different types of polar solvents. One is polar protic and the other one is polar aprotic. And from the structure of polar protic solvents, you can see that there is a hydrogen that is connected to an electronegative atom. So you can see that water has a hydrogen that can easily come off in the presence of a base. And similarly, if you take a look into each one of these, ethanol, acetic acid, and tertiary butyl alcohol, in all of this, you can see that this hydrogen is going to come off, right? Okay, or it has the ability to form hydrogen bonding. Now, in the case of aprotic solvents, you do not have any hydrogen that is connected to an electronegative atom. So here are some examples with structures. The most important, the most common ones are dimethyl sulfoxide, dimethyl formamide, and acetonitrile. Here is the structure for dimethyl sulfoxide. This is the structure for dimethyl sulfoxide. And this is the structure for dimethyl formamide. And in these, you can see that there is no hydrogen that is connected to an electronegative atom. This oxygen is the electronegative atom here, and you do not have any hydrogen that is connected to it. And when you want to draw the charges on these atoms, so obviously the sulfur is going to be electropositive and the oxygen is going to be electronegative. And similarly, the carbon here is electropositive and oxygen is electronegative. Okay, that's something that we needed to keep in mind when we want to understand how the nucleophilicity is going to be affected by the solvent. Okay, now that we know the different types of solvents, let's now see how the nucleophilicity of the nucleophile is going to be affected by the solvent. Now let's say that you're conducting the reaction in a polar protic solvent where I minus and F minus are the nucleophiles. So here are your nucleophiles, and for this example we have taken methanol as a solvent. We already know that methanol is a polar protic solvent, right? Wherein you can see that this hydrogen is connected to an oxygen and an electronegative atom. Now, what happens in a polar protic solvent is the nucleophiles or the stronger bases is going to have better coordination with this hydrogen, or in other words, it's able to form hydrogen bond. This hydrogen is able to have ion dipole interactions with the F minus. Because F minus is a stronger base, it is able to form strong ion dipole interactions here. Now look into this. You want this F minus to be going and attacking as a nucleophile. But then if this F minus is trapped in a polar protic solvent through ion dipole interactions, then it is definitely not available. So in order for the nucleophilic substitution reaction to be taking place with this as the nucleophile, then you have to break these ion dipole interactions. Right? On the other hand, when you take I minus is a weaker base, which means it's going to form weak ion dipole interactions here. So here it would be only weak ion dipole interactions. Or in other words, this I minus is not trapped well enough in polar protic solvents, and therefore it is available for the nucleophilic attack. So on the whole, when you take strong bases and conduct the nucleophilic substitution reaction in polar protic solvent, they are going to be trapped because they are able to form strong ion dipole interactions. And therefore, they are not very good nucleophiles. In polar protic solvent, I minus is a better nucleophile than F minus. Now let's see what's going to happen in polar aprotic solvents. Here are some examples for polar aprotic solvents. This is DMF, dimethyl formamide, and this is DMSO. And let's also draw the partial positive and negative charges on these molecules. So sulfur is an electron deficient atom, and therefore it should have a partial positive charge on it, and oxygen is electronegative, and therefore it should have a partial negative charge on it. Now let's say that you use potassium fluoride as a nucleophile. Okay, so potassium fluoride is going to get separated as K plus and F minus. It's going to get dissociated as K plus and F minus. When you use polar aprotic solvent, the K plus is going to get solvated, which means the DMSO molecules are going to orient in such a way that the K plus is going to get trapped between the DMSO molecules. If I'm going to draw the structure for this, like to clearly represent this, this is how it's going to be. Where the oxygen is going to have negative charge on it, and the sulfur is going to have a positive charge on it, and because of which the K plus ions are going to get trapped between the negative charges. So this is how it's going to be. And because the K plus is trapped, because the cation is trapped, the nucleophile is now freely available, and therefore it can act as a better nucleophile in a nucleophilic substitution reaction. On the whole, we can conclude that I minus is the best nucleophile in a polar protic solvent because I minus is weakly solvated because of weak ion dipole interactions. And therefore it is freely available for the nucleophilic attack. On the other hand, F minus is the best nucleophile in a polar aprotic solvent because it's more polarizable and it is poorly solvated. In a polar aprotic solvent, it is always a cation which is solvated, leaving behind the anion, right, which can act as a nucleophile. And here's a chart that is going to help us to determine the nucleophilicity of the nucleophile in the presence of a particular solvent. So as you go down the periodic table, go down the column, you can see that the size increases and therefore the basicity should decrease, right? Or the basicity should increase in the opposite direction. And this is going to be exactly the same thing as what is happening when you have a polar aprotic solvent. So when you have a polar aprotic solvent, F minus is a better nucleophile. But the opposite is going to be true when a polar protic solvent is present. Okay, so where the I minus is now going to be a better nucleophile and the F minus is a poor nucleophile. So on the whole, the strongest base is still going to be the best nucleophile unless they differ in size and unless they are present in a polar protic solvent. Apart from size of the nucleophile, charge of the nucleophile, and the solvent in which you conduct the nucleophilic substitution reaction, there is also another factor which is going to affect the nucleophilicity of the nucleophile, and that is steric hindrance. If there is any steric hindrance in the nucleophile, then it is going to definitely decrease the rate of the SN2 reaction. Now here there are two different nucleophiles. We have ethoxide ion. This is ethoxide ion. And this one right here is tertiary butoxide. Between these two, which one is a stronger nucleophile? Obviously, it is going to be ethoxide ion. Now, what is the reason behind it? Now, let's go back to our mechanism. What happens in an SN2 reaction? Let us say we want to do an SN2 reaction on this alkyl halide using these two nucleophiles. If we are going to use ethoxide ion as a nucleophile, then it may not have much problem in going and finding this carbon from the side that's opposite to that of the leaving group, because it has less steric hindrance, right? Whereas if we are going to take tertiary butoxide, the tertiary butoxide is already bulky, right? So it will be hard for it to go and approach this carbon, this electron deficient carbon, from the side that's opposite to that of the leaving group, and therefore the reaction rate is going to be considerably decreased because of the bulkiness of the nucleophile. Factors that affect the rate of the SN1 reaction. Here are some of the factors which is going to determine the rate of SN1 reaction. In SN1 reaction, there are two steps, right? The first step is the formation of carbocation, which is the rate determining step. And in the rate determining step, you have only the alkyl halide present. So the alkyl halide is definitely going to affect the rate of the reaction. In general, the tertiary alkyl halides are more reactive in an SN1 reaction compared to the secondary and primary. Why? Because the tertiary alkyl halides will form the more stable carbocation. The tertiary carbocations are more stable compared to the secondary and primary, and therefore tertiary alkyl halides react much faster in an SN1 reaction. And this order here is exactly opposite to that of what we have seen in SN2 reaction. The next one is the leaving group. This is one thing that is common in both SN1 and as well as SN2. Okay, where the weakest base is going to be the best leaving group. Weakest base is going to be the best leaving group. And remember, the iodide ion is the weakest base, and therefore, when you have an alkyl iodide compared with the alkyl fluoride, the reaction with the alkyl iodide is much faster because iodide ion is a good leaving group. And the next one is the solvent. And for SN1 reaction to be favored, we need to have polar protic solvents such as water, alcohol, and carboxylic acids. These are going to favor the formation of SN1 reaction.